Domain shift is a fundamental problem in machine learning, and it arises when the training and test data don't follow similar distributions. The distribution shift can be due to different backgrounds or different styles for the same class of objects, as you see in this figure. Machine learning approaches can hardly handle the domain shift, and so it causes the drop in their recognition performance. Domain adaptation techniques aim to align the source and target distributions by learning domain invariant embeddings, so to tackle the domain shift problem. These techniques all tackle the closed set domain adaptation scenario where the source and target data contain exactly the same classes as you see in the left figure. In the right figure, you can see that target data have additional classes which were not present in the source data. This more realistic and challenging scenario is called open set domain adaptation. All the existing approaches for open set domain adaptation work based on predicting and isolating the unknown target data. However, these methods have to rely on either carefully tuned thresholds to reject the unknown samples, which can be very dataset dependent, or they rely on pseudo-labeling strategy, so rely on classifier trained on the source data, which might not be very effective in detecting unknowns in target data. To overcome these limitations, we propose to complement the source data by generating unknown samples. As you see in this figure, given source samples from known classes and target samples from both known and unknown classes in part A, existing open set domain adaptation methods shown in part B try to adjust decision boundaries to identify unknown samples, but our approach shown in C generates unknown source samples and turn open set domain adaptation into a closed set problem. This is our proposed framework. We introduce a generator G that, given a noise vector Z as input, it produces unknown samples XG. Then we complement the source data with these newly generated samples, and we pass augmented source data and the target data to the feature extractor and extract their features. So by augmenting the source data with unknown samples, we have turned open set domain adaptation into a closed set problem. And now we can exploit the distribution alignment strategies such as MMD-based loss and adversarial domain classifier to align the target feature distributions to the augmented source one. Also, we have multi-class classifier H that encourages the generated samples to be classified as unknown. We apply our approach on 3 benchmark open set domain adaptation datasets called Office Home, WISDA, and Centurial O. We report 2 widely used metrics of normalized accuracy for the known classes, OS star, and normalized accuracy for all classes, OS. Our method consistently outperforms the state-of-the-art baselines on 3 benchmark datasets. For Office Home, OS accuracy is improved by 1.8%, and OS star accuracy is improved by 2.6%. Also in WISDA 17 and challenging Centurial O datasets, our approach outperforms state-of-the-art around 2% on OS, and this is without needing to tune any hyperparameters. To confirm that our generated samples are effective, we compare the distributions of the generated samples and unknown target samples. As you can see in figure A, our generated unknown samples in orange cover a large portion of the unknown target distribution in blue. Also, we compare the distributions of the generated unknowns versus the known classes, and you can see in part B that the generated unknown samples have only little overlap with the known classes. You can see that the unknown distribution somehow complements the known distribution.